सगळं करू ना,
हम्म.
इम्प्लिमेंट करू, जेणेकरून नंतर मुलींना विचारल्यानंतर असं म्हणू नये की त्यांनी आमचं
Good morning to all. With the permission of resource person, shall we start the session? Professor A.G. Patil, sir. Hello.
Good morning, sir. Am I audible?
Yes, sir. Yes.
Okay.
Okay. I request anchors to start the session.
Yes, sir. Am I audible, sir?
Yes, yes, sir. Yes,
Yes,
ma'am.
ma'am.
Good morning to one and all. I a warm and heartfelt welcome to respected resource person and participants to day 5 of faculty development program organized by Sri Siddheshwar Women's College of Engineering, Solapur. Today's session focuses on the highly significant and emerging topic explainable artificial intelligence. As artificial intelligence continues to influence decision making across education, healthcare, finance, and industry, the need for transparency, accountability, and trust in AI system has become more important than ever. Explainable AI plays a vital role in ensuring that AI models are not only powerful but also understandable, fair, and ethically responsible. It is our great honor and privilege to extend a warm welcome to our esteemed resource person, Professor Amul Patil sir, for today's session on explainable AI. Now, I request Professor Annapurna Salanke ma'am to give introductory note of Professor Amul Patil sir. Ma'am, please.
Good morning, everyone. At the outset, I would like to thank Kothari Madam for giving me the opportunity to introduce today's speaker. It is my pleasure to introduce Professor Amol Govind Patil sir, Assistant Professor at Tatasaheb Kore Institute of Engineering and Technology, Varnanagar. With over 25 years of experience in undergraduate and postgraduate teaching in computer science and engineering. He is currently pursuing his PhD in deep learning with research interest in sentiment analysis, depression detection, and AI driven systems from Shivaji University, Kolhapur. Professor Patil sir has published in international journals and conferences, including Springer indexed venues, and is a Best Paper Award recipient in International Conference on Communication, Image Processing and Computing, which was held in March 2025 at Walchand College of Engineering, Sangli. He has also contributed extensively to academic leadership, curriculum development, and research mentoring as a former head of the department, BOS member, and project mentor. As a part of the 1 week FDP on research trends in AI for next generation teaching learning process, he will be delivering session titled Explainable AI. This session is highly relevant to the goals of the FDP and the growing emphasis on transparency and trust in AI systems. On behalf of our institute, I welcome Professor Patil sir for today's session. I thank Preeti once again for the opportunity, and I now respectfully hand over the session to Preeti ma'am for further proceedings. Thank you.
Thank you, ma'am. We are confident that today's session will be highly informative, inspiring, and beneficial for all attendees. Once again, we extend a warm welcome to Professor Amul Patil sir, and we sincerely thank him for sparing his valuable time and sharing his expertise with us. Thank you, sir. And now I to request sir to take over the session. Over to you, sir.
Okay, thank you, ma'am. Let me share my.
Hello, is my screen visible?
Yes, sir.
Yes, sir.
So
Yes,
shall we
sir.
begin? Shall we begin?
Yes, sir, sure.
At the outset, I'd like to thank Siddheshwar College of Engineering, Women's College of Engineering, Solapur, and also like to thank Professor Amol Phatak sir for providing me an opportunity to share my views and to have an interaction on the explainable AI. Now, the motivation for explainable AI is necessary because we are all together working on the artificial intelligence and machine learning models. The most of the artificial intelligence and machine learning models provide accuracy, speed, automation for the predictions. If the prediction is correct, these models are giving the prediction. If the prediction is correct, we usually stop there by indicating their accuracy, their precision, F1 score, and so many metrics. But the problem lies here that the modern AI models, such as deep neural network, ensemble models, transformer models, they have millions or billions of parameters. They learn complex and hidden patterns. And moreover, they do not explain why they had made a decision if the a particular prediction is correct or not. So you can see in the visuals in the general AI that is deep learning or ensemble networks or transformer networks or pure machine learning model, we simply provide the training data set and the artificial intelligence model. They learn the functions and the features and they give the decisions or the recommendation. But they are not justifiable. Why these results are coming up, how these results are coming up, what has contributed to take that particular decision or to classify the particular input sample. Whereas the explainable AI works along with the artificial intelligence model, we say that it's not a new model. We say that the new AI model process where we include the explainability and we answer the above questions, why it has happened, how the decision has been taken, and what classification is done. So these networks have the complex and hidden patterns and do not explain why they had made the decision. So we need the explainable AI. The model predicts X is the output, but why did the model predict that particular X output? And this is necessary in the most of the AI applications. We'll see the applications and the case studies in later on. Now, what is explainable AI? In real system, the decision affect the humans. For example, we deal with the doctors and we feel ourselves as a patient, and the patient's treatment is the dialogue between the doctors and the patients. So patient's treatment, if the doctor has diagnosed a particular disease, then the doctors, the clinicians has to support their decisions for the diagnosis. Similarly, for the student's admission, why the student is taking the admission for engineering college or various professional courses, and which features and factors has affected for that particular student based on the colleges. Or there are various parameters, various kinds of attributes for that is related with the admission for the students. Then the most important is the loan approval. Whenever the banking agencies or any financial institutions are giving the loans to the person, they not only just see the salary slip, but they evaluate the loan applicant on the various parameters such as the various lender score and number of loans he is prepaying, and they are finding out whether the loan can be repaid in a defined duration or not. Either legal or hiring decisions, this is also needed. Why a legal case has been handed over and why the hiring decision has been taken for that particular person who is appearing for that particular candidature. If we cannot explain the decisions, whether the decision is classified in particular class or whether the recommendation has been given, then we cannot trust it, we cannot debug it, we cannot audit it, and we cannot legally justify it. So therefore, explainable AI answers all these particular questions. In current scenario, simply AI is no longer enough. So we need AI plus explanations about their decisions. That is nothing but explainable AI. Now let's have a short discussion on this. What is AI and what is XAI? AI typically classified in the broad terms as a black box model, glass model, or no box model. So we know that in the black box model, they hide the internal details of the model. That is how many parameters that you are taking, how many layers are you using, which are the attenuation parameters, loss functions. So all these internal details are skipped. The glass box model analyzes the maths, models the relationship, and no box, they are simply mathematical calculations such as y is equal to x, x raised to b. So they give enough math to demystify the algorithm and relate the key biological concepts. So typical AI focuses on prediction, whereas the XAI focuses on the traditional prediction and the reasoning for that particular results. The models, they are often black box in AI, whereas in XAI, the models are black box and the explanation. Black box here means hiding the internal details. You just know the input and you just know the outputs. In AI, the trustworthiness of the model that we are developing, we are designing, they are implicit. That means we are getting a particular classification is done. Whereas in explainable AI, it is explicit. It is giving the reason behind that particular decision. So debugging in the black box is very difficult because the internal details are not clear for us. Whereas explainable AI makes the things easier. The regulation task is very weak for the AI, especially in the healthcare industries, whereas explainable AI has the strong support for the regulation. In artificial intelligence kinds of models, the human role is very passive, just to submit the input and find the appropriate classifications. Whereas explainable AI, it has the human role for the active participation. The black box models such as ML or DL model take the input data in terms of various ranging, EHR, imaging, or the sound waves, etc. They extract the features, they perform the analysis on those features, and they are visualizing the results in terms of the final output. Now here we are adding the explainability. Why did that model decide on a certain prediction and we are getting the output prediction? So this is in nutshell how the explainable AI should work. We are aware about various other AI techniques. Let me go to quickly in those particular techniques. The specific one in the machine learning, we have the rule-based AI, where the human written rules are utilized. For example, for a loan sanction or a simple application, if the income is greater than an X amount and the credit score given by the lenders is greater than Y amount, then we have to approve the loan. Here we are putting the two conditions which are collected together as a rule. They are fully explainable but not scalable. Only income and credit score, these conditions are not sufficient. The classical machine learning models such as linear regression, decision trees, SVM, KNN some are explainable and some are not. Whereas we get the decisions, we are getting the classifications, and we are getting the different kinds of results, what we are expecting and why that model has been implemented. The third classical technique is deep learning, where we use CNN, RNNs, and transformers, where we plot the accuracies, where we plot the error metrics, why the model has given the accuracy above 90%, 80%, and so on, by using test split kinds of methods. So deep learning models are extremely accurate. The accuracy is very, very high in the deep learning models, but they are almost completely opaque. Why the decision has been taken for that particular input is not known or visible to the users. Some terms are used in the explainable AI. The meaning of explainability is the ability to describe the internal mechanics or the decision process in human understandable terms. It does mean that if the loan was rejected, we specifically ask the reasons why the loan has been rejected. There could be several parameters or there could be several reasons whether the income and repayment history has contributed negatively. The person's income is not stable and the credit score is not also good, whatever the benchmark has been set by the lending agencies. So therefore, we require the explainability why the loan was rejected. This is the negative aspect of the classification. Then whenever we are getting the results, the interpretability is introduced in the explainable AI, the degree to which the human can understand the cause effects in the model's decision. If my loan is accepted or whether my loan is rejected. If the loan is accepted, there is less interpretability. But if the loan is rejected, there the human or the lender needs to ask why my loan is rejected. Some examples in this interpretabilities, we can typically use the decision tree, high interpretability deep neural network, and this deep neural network has the low interpretability. So we use decision tree for the high interpretability and deep neural network for the low interpretability. Then we need the transparency. So whenever we have the transparency, then we have the trust on the model. The transparency addresses how open or accessible the model, the inner things are. So if we use the linear model, such as the regression, they are transparent. But if we are using transformer kinds of model in NLP, such as BERT binary encoded transformers, then they are not transparent. They are not transparent. Why they have taken the particular decision on a particular paragraph and why this particular paragraph has been classified as a false reviews or not. The scope for the explainable AI to distinguish the product level explanations, why this prediction has been made versus the model level, how the model behaves overall. So these two issues has to be addressed for the explainable AI architecture. A model can be accurate but not interpretable. Typical ML, typical DL models, they are very, very accurate. They give the desired results, but they are not actually interpretable. A model can be interpretable but less accurate. So it is such as decision tree is giving you the higher interpretability. Random forest give you the higher interpretability, but they are not as accurate as the deep learning is. So what XI is, XI bridges this gap. The model is accurate but not interpretable. The model is interpretable but not accurate. Why this explainable AI is coming into picture? The goal is, as the anchor said, the trust, debugging, fairness, compliance, user control, knowledge discovery. So these are all necessary tasks because we ask many times the questions if the decision is in favor of us or decision is in not favor of us. So we need some trust. We need debugging why this particular result has appeared, whether it is fair enough to compare the various parameters and whether it is fair enough to compare with the historical data sets. The compliance, if something is missing, if the loan is rejected, and if you are, the banking personnel has asked you fulfill some of the parameters, then that compliance can be covered. It has the user control, that is in terms of input. The user can control the input in the controlled environment, and finally, the user gets the knowledge discovery. The stakeholders are many more. There are developers, domain experts, regulators, and the end users. The explainable AI explains the changes depending upon the stakeholder. For a stakeholder developer, they want the debugging the model, why this error has been encountered, whether the resources for to execute this particular code is sufficient or not, or which resource has played the significant role for debugging or for executing that particular project. The domain experts are necessary. They want to validate the logic, why this decision has come, which logic has contributed for that particular decision is used by the domain experts. The users, as I said, in the loan applications or the patients in the medical history, healthcare systems, they need to understand the particular decision, why the doctor has prescribed me these medicines, why this particular decision has been taken, mainly because of pathological report or clinical investigations. We require some regulators, such as the regulatory bodies. In the medical science, there are regulatory bodies. In the financial, there are regulatory bodies. So these rules has to be satisfied, which ensures the fairness among the decisions. Some taxonomy of explainable AI. The explainable AI has been categorized in various categories: intrinsic versus post hoc, global versus local, model specific versus model agnostic. The intrinsic model is explainable by its design only. For example, regression. For example, logistic regression in the machine learning. So linear model, decision trees, they are self-explainable. If we have the plots for that, we can easily understand that why the decision has been particular taken up. In the post hoc methods explain after training. Once we train the model on the particular data set, and it explains why this decision has been taken up. Normally we use the deep learning techniques in the post hoc kinds of models, XI models. Some examples that explains our decisions such as SHAP and LIME. I'll be covering some case studies of the SHAP and LIME in latter part of my presentation. The global versus local. The global explanation, it focuses on the overall model behavior. How does the model behave overall? Whether the accuracy, precision, or F1 score is correct or not. We are fully relying upon the evaluation metrics, such as the feature importance across all data. So if we are having several features, for example, the breast cancer detection or the pneumonia detection, we have chest X-rays, we have mammographies, we have biopsies. So we have to evaluate among various kinds of parameters and the features, and which feature has contributed a lot for the across all data sets. The local explanation, why the specific, a single condition, single prediction. Global explanation, the entirely a model. The local explanation focuses upon why the specific prediction has been occurred up. For example, why this patient was classified as high risk. There could be two patients which are giving the symptoms of pneumonia, but one of the person is having the high risk and one of the person is with the low risk. So why the person classified as a high risk? It has to be classified, but classified for that particular example. This is known as local explanation. The model specific or model agnostic, this is also one of the classification. Model specifics uses the internal structures, that is number of layers, the parameter tuning, hyperparameter tuning, weight adjustments, back propagation. So these are internal structures which are known to the developer, designers, and the programmers as well. Such as we use the gradients in the neural network. Gradients are calculated and they are propagated to reduce the number of errors so that the accuracy can be high. The model agnostic treats the model as a black box where the internal details are hidden, and they just explain which parameters or which feature has the significant role to provide that particular results. So we get the three kinds of taxonomy, three kinds of categories for the explainable AI. Now let us understand what is the meaning of intrinsic explainability. I already said that this is the decision tree. This is decision tree that we are learning from in our academics. If the decision is has the left branch, right branch, and center branch, based on the weight, height, and whether the understanding the risk of heart attack. So this is a common popular example of the decision tree. It models by equation y is equal to b naught plus beta 1 x1 plus beta 2 x2, where each coefficient shows the direct contribution. So beta naught, beta 1, beta 2, they are coefficients and they shows the direct contributions. And they are very easy to explain. So we typically use this model in our classroom and we explain to the students. And it has limited expressive power. Just we are understanding high risk of heart attack or not, or this is gone. The decision tree, in the decision tree example, each path is a rule This path can be easily understood by the humans, and anybody can understand this particular hierarchy, the tree-like structures. But if this tree is very large, the tree grows exponentially, the understanding becomes very complex. In the post hoc methodology, we typically use the black box models. They cannot be directly interpreted because they are considered as a black box. How many hidden layers, how many input layers, how many connected layers, which are the activation functions, which are the normalization functions, they are all hidden from the user. So we explain this model is black box, and so we explain it after training. Some examples of random forest, we are using the random forest, which is an ensemble model, and to that random forest, we add the SHAP analysis for that particular understanding, because random forest is very much complex than the decision tree. The SHAP is applied after training and understands which are the parameters, which are the features has contributed. It has the strength, this SHAP works with all modern AIs, and it is flexible too, because it is mathematically derived, and we have different kinds of libraries available in MATLAB or available in Python, and we can utilize those libraries. So it's a very, very flexible. But the biggest weakness of this SHAP analysis in the post hoc explainability, it works with the approximation, not with the ground truth. So that is what the major problem, major weakness of the SHAP. Some of the post hoc methods for the black box model, which are addressed in variety of literatures such as LIME, SHAP, integrated gradients, GradCam, counterfactuals, and anchors. In terms of global and local explainable, global means how the entire model behavior, and then in local explanation, why a specific case. For the specific case, the decision has been taken up. For the global explanations, we use the SHAP plots, which shows the collective contribution of all features for that particular classifications. But in line explanation, line explains for one instance, if the person is classified as a depressive, if the sentiment is classified as a negative, why that sentiment is negative, why that person has been classified as the depressive. So explains only one condition, explains only one case. The global explanation explains the general behavior of the entire model, and here in the local explanation, perturbations are necessary. Perturbation means adding a controlled noise in the output data. So if we add the controlled noise, how my model will behave for that particular decisions. The global explanations are typically used by auditors, designers, and the policymakers, and the local explainability is used by doctors, loan applicants, end users, and so on. In the global explanations, we have the example has been given for the feature contribution class A and class B. Feature 1 in that particular graph, in that particular plot, we can observe that feature 1, feature 2, feature 3, feature 4, feature 5. The feature 1 has contributed less for class B and contributed more for class A. Similarly, feature 2 has contributed more for the class B, and the feature 2 has contributed very less for the class A, and so on. In the local explainability, the probability of class A is 0.33% and the probability class B is 67%. So for the probability of class A, the feature 1 has contributed very less, and the feature 2 has contributed very less for the class B. Similarly, we can explain for the other features as well. Another category is model specific versus model agnostic. Model agnostic means treat the model as black box, as we already discussed. It uses the LIME and SHAP explainability. We only need input and output pairs. There are various models we can see in this particular infographic. The model A, model B, model 3, they are combined with one of the optimization technique, and we get the interpretation B, interpretation C. So this is the collective result for interpretation A, collective result for interpretation B, and collective results for interpretation C. Whereas in the model specific, model A contributes only for interpretation A, model B contributes for the only interpretation B, and similarly, the model C is contributing for the interpretation C. So model A is responsible for result A, model B is responsible for result B, and model C is responsible for result C. So these are individual techniques. So they typically use the gradients. They require differentiability and cannot work on the random forest because random forest is an averaging. It's an ensemble kinds of model. So they cannot work. The model specific technique cannot work on the random forest kinds of AI techniques. In the explainable form, what it contributes, the feature contribution, counterfactual, rules, and the visualization. Feature contributions is understood by the SHAP. The counterfactual, if the income is increased, initially income was very less and the credit score is also very less, so the loan is rejected. If the income is increased by different variety of sources, so what the decisions should be taken? What should change? Whether the decision for the loan approval should be changed or not. So these human questions can be answered by using counterfactual kinds of explainable AI. The rules, we can use the decision tree, why that logic was used, why the heart disease probability has been discovered through these decision trees. In terms of visualization, GradCam technique uses the heat maps or other kinds of techniques where the concentration of these data points is very high and it answers why this where this model particular look. So visualization techniques is used in GradCam. The model specific techniques, the models are interpretable by its design, such as regression, such as logistic regression, decision trees, and some of the clustering algorithms. The model agnostic, also known as post hoc, they work with the black box models such as CNN, RNN, and transformers. We are less aware or we are not aware about how the CNN or RNN is being implemented internally. Then we use the LIME for the local interpretability model. So LIME works on the model agnostic kinds of methods. So they approximate black box model locality using a simple model. SHAP performs the analysis. SHAP stands for Shapley Additive Explanations. They explain the local, they explain the global conditions. Local conditions, individual or patient's post. We can see the chest map for an individual post, individual particular patient, and from that the feature can be identified. This is the heat map kinds of feature. And by understanding the heat map, we can conclude that the person's chest is congested. So this is local explanation. Then the gradient-based explanation method again uses these kinds of heat map. So we have the two types, saliency map and GradCam map. Saliency map shows which part of the input most influenced by the model's prediction. So we are focusing on the congestion for the chest, or we are focusing on the tumor conditions on the brain. This is typically used in the healthcare industry for that particular person. So the GradCam produces gradient-based explanation methods, produces the heat map and identifies or highlights which regions of the image has contributed for taking particular decision. Then the counterfactual explanations, what needs to change for a different outcome. Initially, the outcome may be negative. If we add some input parameters or if we change the input slightly, then how it will affect for the final outcome from the rejection to the acceptance for the loan applications. And simple rule-based explanations. So we use the rules. If height is this and the weight is this, then the body mass index is this, then the person has the probability for the heart diseases. So I'll drive through one single running example that I'm talking again and again, which is a very simple example. The problem definition in the real world context for the loan approval, the person applies for the loan, the agencies perform the home search, then the loan application is being scrutinized on the various parameters and various features, and the loan approval takes place, and after loan approval, finally loan closing happens. This is a binary classification problem where it predicts whether the loan application should be approved or whether the loan application should be rejected. So we have only two classes. If it is approved, what parameter based on which features the loan is approved, and based on which features the loan is rejected. The input feature, that is what bank knows through the loan application and for the home search, whatever the bank personnel has identified these features. And whenever they obtain the features, they create, this model creates the feature vector X, where X1, X2, X3, X4 These are the features which have been extracted from the loan applications and from the personal details by the banking or financial institutions. So in this example, we are using age as a X1, income as a X2, credit score as a X3, and existing loan as an X4, which shows the current liabilities. So if we take some example, if the age is 28, income is 30,000, and credit score is 620 out of 900, and it has existing loans 3. We can clearly understand that based on this particular parameter or feature value, the loan has to be rejected. This is ground truth. So why we need a model? If we use the simple rule like if income is greater than 43 and credit score is greater than 700, the loan should be approved. So this is the minimum benchmark that should be satisfied. So this rule fail in real life because only income and credit score is not sufficient. We have to introduce few more features to justify or to trust for that particular reason. So the relationships are linear, interactive, and the data dependent. Why it is non-linear? Non-linear in the sense the age and income cannot be justified, or the credit score and the income cannot be justified. And if we compare all of these parameters or all of these features, they are typically unlinear. These features are interacting. To whom the financial institutions are sanctioning the loan? The person who is having the young age or the middle age, not for the retired persons. So age is also interactive, performing interactive value. If the existing loans is 3 and the income is very, very low, then also the loan should be rejected. And it is purely data dependent. So how many loans in the such kinds of cases has happened in the past, and to whom we had sanctioned the loan or to whom we have rejected the loan. So hence we use the random forest here for this complex relationships. When the random forest, the data set is going through the forest one, the independent trees, there are n number of trees. The first tree is giving you the result 1, the second tree is giving you result 2, and the nth tree is giving you result n. So all of these results are aggregated towards, average towards, to get the final decision of random tree. Now here we require the explanations. Which parameter or which of the best voters, result 1, result 2 are in the favor and result n is not in favor. So which are the results from the random forest which has given the final decision or final classifications? The decision tree, just we have seen the rule previously. If whether the credit score is greater than 650, whether the income is greater than less than 35,000, whether the existing loans are greater than 2 or not. So based on that, the decision tree takes the decision. And in this random forest, each tree gives a vote, and these votes are average, ensembled. If there are T trees, then Y cap. The final result is summation of all these trees for the f of x. F of x is the function for which is defining the probability for the acceptance or for the rejections. So f of x is f of x for a particular tree is belonging to either 0 or 1. 0 means not favorable, 1 means favorable results. So the output, we average all of these results together and we get the final results. Suppose in this example, we use the 100 trees and 78 trees vote for reject and 22 trees vote for approve. Then the probability of approval for the particular loan in the example case, running case, is 0.22. So that the final decision is rejected. But the forest predicts well, but we don't know why. Which tree has contributed, which feature has contributed for this negative, for this probability of approval is very, very less. So this is a typical black box problem, which has been addressed by this explainable AI. Now we apply the line local interpretability model, agnostic explanations. Why it is local? Because we are considering only one case. We know that the black box models, that is random forest, performing very well based on the voting or based on the ensemble techniques. The output also, we know that f of x is giving you the loan rejected for the example that we had for the data points that we had taken. And you may ask, why this loan has been rejected? I am young enough, age is 28, income is fairly enough, that is 30,000. Credit score is in between good to average, average to good, and we have very less kinds of existing loans. So is it my age that the loan has been not sanctioned? Is it my income, or is it my credit score, or is it my existing loan? So this random forest or decision tree is not identifying why this loan has been rejected. The model cannot answer. The core idea behind Lime is around one specific data point, even a complex model behaves approximately like a simple model. That means for a one specific data point for this a particular loan application, it has to answer the questions why, which parameters, and why this loan has been rejected. So this is local assumption for a single case, for a particular case. So we say that local cannot be equal to global. Global means overall in the entire data set. If we train that particular model for the given data set, the model behaves accurately. The model gives a very high accuracy. But in terms of the local model, how the model behaves for near to one instance among that particular data set, or among the sample case which is not present in the data set, whether the model behaves as per our expectations or not. The Lime explains not a whole model, but only this decision, why this decision is favorable and why this decision is not favorable. So let us apply this, the Lime workflow. It has 6 stages. Select one instance to explain the example that we are taking, the loan rejection example. Generate nearby synthetic samples. Remember this step, step number 2. The Lime uses the perturbation, that is, it is creating synthetic samples nearby that particular example. So we see that in the visual, the red dot is the case that we are considering, and it is finding out the neighbor search with the depth 1 and identifying the various kinds of the synthetic samples. The synthetic samples are producing the different kinds of the vectors x1 to xn for the sample 5, x1 to x1 for different samples, and so on. So this information aggregation is used by the Lime. So they query on the black box model because the Lime not necessary to have the internal details, how many layers, which technique, ReLU function or tannage functions, averaging functions, we are not interested. So these the samples are weighed by their closeness, that is k nearest neighbor samples has been used. Hit a simple interpretable model and use the model as an explanation. The pipeline is like this. On the test data, we are using the test instances by using train test split kinds of method. That is 80% for the training or 20% for the testing, and so on. 70-30 or 60-40 kinds of splitting has been done. After the test instances, after the model has been trained, the random data perturbation, the concept of perturbation is nothing but adding some kinds of noise or adding some kinds of modifications in the input. And this input, after I modify this particular input, what happens, that particular results. So the new synthetic samples are weighted. The labels for the predictions for the new samples has been identified, and then model is trained. And based upon the model training, or the model has been giving the output, the features x1 to xn features has been identified, which feature has contributed or which feature has not contributed for the decision. So that is explained here by using Lime. The user gets the answer why my loan has been rejected, why I am detected as a cancerous person, why the particular brain tumor is harmful for me or not. So they explain that particular user or particular person. Now let us apply some mathematics on these Lime steps. In the step 1, the instance to explain, we know that the feature vector is 28 is the age, 30,000 is the income, 620 is the credit score, and 3 is the number of loans. So we apply general perturbation, that is Lime creates some synthetic samples around the given data, age 28, income 30,000, then credit score is 620, and the active loans is 3. These samples are not real applicants. They are what if variations. So this synthetic samples has been created. Why this necessary? Step 2 is necessary. The purpose is how does the model react if we slightly change the inputs from the known patterns. Then we move for the step number 3, query the black box model. Each perturbator sample is passed through the model. These are neither in the dataset nor in the train set or nor in the test datasets. They are random samples. So these samples are passed to the model, and for each sample f of x is whether probability of approval is coming because of this x parameter or not, that we are identifying. So we get in the step number 4, that is the proximity weighing. So for this particular samples, so we can see in this particular table, the synthetic score has been created by this line. Age 27, 29, 30, 28, and 30. 4 age groups has been considered, and the incomes is slightly varied. Our input is 30,000 for 28 age. Credit score is also varied around this particular data, slightly variations. Our example is of 620, and the credit score here given from 610 to 600 to 640. And the number of loans is also varied. This table is not present in the data set. For the sample 1, the model outputs 0.18, that is the probability of rejection, not approval. For the sample 2, the probability is 0.24, again rule rejected. For the sample number 3 above, the loan probability is 0.40, and for the sample 4, the probability is 10. So we are averaging all of this, and we are comparing the results with our input, that particular data set. So the line assigns the higher weight samples the closer to the original point. So closer to the original point is 28. The closer to original point is 28, 27, and 29. One age group is higher, one age group is lower. So it assigns higher weight for the age group 28 and age group 27. The weight function is applied like this: pi x naught of xi. Xi means whatever the synthetic samples the line has generated, and it is calculating the weight function by using exponential derivations. What this means? This means that the close samples to the original data set, that is x naught, they have the high weight. Far samples such as 30, age group 30 has the low weight, and this enforces locality. What has happened with the similar age group particular persons with the different incomes, different credit scores, and different number of loans parameters. Fit this interpretable model. Line fits the simple model g of x. Usually the g of x is w0, w1 x1, w2 x2, w3 x3, and w4 x4, where w's are the weights calculated as above using the weight function, and this x1, x2, x3, x4, these are the synthetic samples that line has generated. This model is trained to mimic the black box locally. So what is happening internally is not known to that particular person, but we say that there are different cases, 1, 2, 3, 4, and for all of these cases loan has been rejected. So therefore this loan can be rejected. So it explains only local conditions. The Lime objective function, Lime solves the equation, the erg minimum. So it's a loss function, local fatality, loss of g, f of g comma pi x naught and omega g, that is interpretability. So it combines local fatality plus interpretability, where f stands for the original black box model, g stands for surrogate model, that whatever we had averaged previously. So this is the g of x is equal to w1 etc. L is the loss function. So difference between f and g, what f has been doing originally and what g function is doing after introducing the synthetic data. Pi x naught is the locality weighing, that is the weight equation. Omega g is the complexity penalty, keeps the model simple, avoids overfitting or avoids underfitting for the particular model. So omega g is necessary for the complexity penalty. Now Lime trades the global accuracy for the local interpretability. It does mean that for a particular example, if the loan has been rejected, for the similar cases, loan should be rejected. So this is the global condition for a single case to overall the global, a particular set of users having the data values nearby. And finally, the Lime explanations, the final score. The final score is been calculated like this for our example. The credit score is 620, existing loans are 3, income is 30K, and age is 28. The final contribution for the credit score is 0.38 by using this Lime equation, and existing loans is minus 0.27, income is minus 19, and the age is plus 0.06. It does mean that only the age is the feature which is contributing the favors that loan should be sanctioned. Early age having the capacity of repaying. But for that particular person, the credit score has the negative contribution. Existing loans, that is number of 3 loans, has the negative contribution, and the income is very less, has the negative contributions. So because of these 3 parameters, these 3 features, the loan gets rejected. So final Lime explanation is like that: 0.50 minus 0.38 minus 0.27 minus 0.19 and 0.06. So which comes to be the probability of 0.22, which is far less than the approval. So decision is loan rejected. Now, if you plot the graph and if we encode this particular program using Python or MATLAB, the prediction is loan rejected. So we have the probability that credit score values has given the contribution 0.38 minus negative 0.38, and the existing loans is negative 27. Income is on the boundary plus 14, and the age is 28 plus 0.08. Some example randomly taken from this particular Python program particular code, and we see that the credit score and existing loans, they pushes the decision further towards the rejection, and the income and age, they pushes the results slightly towards the approval. So we understand from this particular plot that credit score and existing loans are the major contributors why the loan has been rejected. What Lime does, as I said, the Lime builds a local surrogate model around one applicant by computing some synthetic data points. This bar shows the feature-wise contribution to the rejections. Credit scores and existing loans are dominant for these particular decisions. This explanation is valid only in the neighborhood of these particular applicants. So we are considering not all data points, only neighboring data samples and data points for the given example. So in a nutshell, Lime explains a single decision by approximating the black box model locally with a simple and interpretable model. The second technique that is used in the explainable AI is the SHAP, which is most popular than the Lime because the SHAP handles both the global explainability as well as the local explainability, whereas Lime handles only local explainability. The SHAP explains the predictions by fairly distributing the model's output among the features using the Shapley values from the game theory. So SHAP is designed from the game theory. So we have the team games such as the cricket or such as the soccer, where if an individual player plays on very good, but the game cannot be won. If all the players is contributing equally, then the game can be won. So we can see this particular visual over here. It's a particular game around the seven players. There are some players which are having the no contribution. There are some players has the medium contribution, and there are some players which are giving the good or total full contribution. So all of them are averaged and found out the base value. The base value is expected model output when no feature information is known. So based on the player, based on the conditions, the India should win today's match. So this is the expected model when no feature information is known. Which player is contributing, whether Hardik Pandya is contributing or whether the Kuldeep Yadav is contributing, we are not aware. But we know that the base value is nothing but the expectations. So this is known as phi naught is equal to expectations of f of x. The Indian team is playing semi-final today, and the Indian team has to win to go for the finals. So this is the expectations. In our loan model, suppose for across all applications in the data set, the phi naught is 0.55. it does mean that 55% among all the applicants, 55% chances of approval. The model predicts 55% chances of approval. 55% people get the loan sanction, whereas remaining 45% of models, 45% of people get the loan rejected. If we consider the analogy of game with our loan application, the players are like input features, age, income, credit, scores, and loans, whatever we had considered, X1, X2, X3, X4. The game is nothing but making the loan approval predictions, whether the loan is approved or not, similar to a match. A match should be won or match should be lost. The reward is the model output, which approves the probability or around which player the particular game or around which particular that particular feature the decision is in favor or decision is not in favor. So fair payout is SHAP value for each feature. SHAP calculates the each player's or each feature's contribution in that particular decision. How it works? By using SHAP additive explainable model. SHAP represents the predictions as f of x is equal to phi naught, summation of 1 I is equal to 1 to m and phi I, where f of x is the prediction for this applicant, for the current applicant that we are considering. Phi naught is a base value is already calculated here, that is phi naught 0.55%. It does mean that 55% loans are approved. So we can take this as a threshold as well. Phi I is the SHAP value for all features, feature I. So we are having 4 features. So for the SHAP value for all 4 features has been computed using these particular equations. M is the number of features. In our example, the features M is equal to 4. So this additive property is critical and unique to the SHAP. So therefore, SHAP is popularly used. So it interprets that negative SHAP decreases the approval probability and the positive SHAP increases approval probability. Now, similar to the line, we have the features. Same features is carried forward in the running example. Credit score, existing loans, and the income and the age. For each of these features, X1, X2, X3, X4, the SHAP value phi I is computed. Credit score gives you minus 0.40. Existing loans gives you minus 30. Income gives you minus 20. So these first 3 features pushing the result or pushing the decision towards the rejection, whereas age is equal to 22 has the positive SHAP value, which pushes the decision for the approval. Since the 3 parameters are contributing negatively, so the result is negative. That is, loan has to be loan should not be approved. So final prediction calculations and their contributions based on this table and the computation that has been done using some Python libraries. So we aggregate this together over here. So f of x final prediction could be given as 0.55. 0.55 is the probability of entire model loan gets sanctioned. Minus 0.40 credit score, the negative player. Minus 30 existing loans, negative player. Minus 20 income, negative player. And age plus 0.07 is a positive player. If we sum up this, then we get 0.22. This is the final probability for the SHAP value. So approval probability drops from 55% to 25%. So if the approval probability is greater than 55%, it does mean that loan is approved, and the aggregate probability is falling down towards the 22%, so the loan is rejected. So because of your credit score, because of existing loans, and because of incomes, your loan has been rejected. The SHAP values exactly sum the difference between prediction and the base values. So base value is very, very essential for the SHAP calculations. SHAP computes each feature's contribution as average marginal contribution over all possible orderings. So the equation is very, very complex. So based on the factorials and how this particular value has been calculated, why this 0.40 is coming up, why this 0.30 is coming up, why this 0.20 is coming up, is because of due to this particular equation. Where yes is the subset of features, we have 4 features over here, and the n is also all total number of features. If the total number of features are 10 and we are considering only the 4 features. Again, we plot the previous calculations using the shape plot. We see that the base value here, we can find here the dotted line, which is 0.22 and 0.55. 0.22 is the rejection and 0.55 is acceptance. So if the contribution is towards the negative direction, it does mean that the loan has to be rejected. And if the contribution is towards the positive direction, that is up to 22%, it does mean that loan should be accepted. So the age is pushing the loan towards the approval, whereas credit score, existing loans, and the incomes shown by the red color pushes the result towards the rejection. So F is equal to 55 is the base value. So we are comparing all these particular contributions based on this particular 55%, that is base value. F is equal to 55. It means that if the model know nothing about the applicant, it would predict a 55% chances of loan approval. That is the meaning of base value. So this explanation describes the model's behavior, not the real world or causality. So this is called as the global explanation, how the model should be behaving based on the features that we had chosen for. So this is about, in summary, in nutshell, what the SHAP is doing. I'll take one more case study, that is the breast cancer detection. So from the clinical basics towards the model to the line and to the SHAP. So this is the flow for the particular case study. For the breast cancer, the clinical process is getting the imaging, that is mammograph or ultrasounds. We can take some biopsy as well, tissue samples which has been extracted for the affected region. What the doctors will visually inspect to detect that particular whether that mammography is resulting in the breast cancer or not. So they understand the size of nucleus from the mammography or ultrasound diagnosis, whether the shape is irregular among the all other previous samples that the doctor has observed, what is the boundary roughness, and what is the compactness and the symmetry of that particular image. So some sample images that I had shown here for the mammography, ultrasound, and the pathological cell examinations. The doctors detects cancer by visually inspecting the cell structure and irregularity, because they know already the previous kinds of samples, which are the non-cancerous cells and which are the cancerous cells. Now this becomes a data set for the doctors and for our model as well. The ML model does not see any image, whereas image needs to be converted into numerical features. So we are giving the images, the image patch, and from that image patch, we are creating the features that we are interested in to detect whether the breast cancer can be detected or not. If it is detected, what is the severity? So dataset in this particular case study is used as breast cancer Wisconsin diagnostic datasets, where 569 patient samples are present. 30 numerical features are used, and binary target is 0 and 1. 0 is malignant cell and 1 is benign cell. Malignant means affected, benign means a normal cell. The features used in this particular case study is each nucleus is describing 10 core measurements, each with mean, standard error, and worst value. So these 10 measurement, 10 features have these 3 values: mean, standard error, and the worst value from the data sets. 4 features that we are identifying in this example, in this case study. These are the numerical features represent exactly what pathologists observe visually, such as radius, that means size of nucleus affected region; perimeter, that is the boundary length for the affected cell; area, the cell size; texture, the surface roughness; smoothness, the boundary regularity; compactness, the density; concavity, the indentation; and the symmetry, the shape balance. So all these features are observed by using some ML or DL kinds of applications. Again, here we are using the random forest classifier to understand very effectively which decision tree has contributed for the malignant cells, or which tree has contributed for the benign cells. Why the random forest has been used? The same answer that we had taken for the loan application. It handles the non-linear relations. It is robust to the noise. If we add some unseen patterns, or if we perturbate some input samples, then this is the tendency how the model should react for this particular input noise. It uses the strong baseline for the medical data. Decision tree 1, decision tree 2, decision tree 3, decision 3. They are voting independently. So we are taking, in the medical terms, we are taking the second opinion, third opinion, and so on. So if all the opinions are giving you the negative results, then we can aggregate, we can ensemble that particular things that the person is having the malignant cells. So the prediction task is f of x is benign or malignant cells. So majority voting, one doctor says no, it cannot be a cancerous cell, but 3 doctors says that yes, it is a malignant cell or cancerous cells. So majority voting is been used here for the random forest classifier. Random forest classifier is a representative example for the ensembles. We can use different kinds of neural networks, RNNs or deep neural network DNNs, and we can get the various output parameters, output probabilities from various CNNs, various DNNs, and various RNNs. Also, we can use some pre-trained model which transfers the pre-trained weights to the CNN that we are considering for. Now take one example for the patient. One patient is which is using considered as a fixed example, and based on these features, the output is malignant. The feature that we are considering here for this case study is mean radius is 17.9, mean texture is 10.4, mean area is 980, mean concativity is 0.19, and mean smoothness is 0.10. So we are not aware among all of these features which are driving that the cell for that particular person is malignant or not. But the model has given the output malignant. Now we want the answer. Why the model classify the patient as malignant? So therefore, XI is needed here. So XI is needed here. Why? Because a black box issue. So deep learning or the random forest classifier, they are black box kinds of techniques in the AI. So they are just giving me the classification, whether malignant class 0 or benign, the class 1. But doctor cannot trust the model says malignant just by observing the mammography images or observing the ultrasound images. The doctors cannot say that you are having the cancer indications. What it needs which feature is critical for declaring this cell is malignant. How it is strong? If the feature is saying that the cell is malignant, whether that particular feature is strong enough to trust build. Is it reasonable? Whether it is reasoning appropriately that this strong feature is giving you the results such as malignant. So this motivates the LIME and SHAP. LIME for the local explainability, and the SHAP can be used for the global explainability. In the LIME explainability, that is local, whatever the example that we are considering. What LIME does, as in the financial case, it perturbs the patient data locally. It means it is creating some synthetic data points near to the sample under considerations, and it fits the local linear surrogates. It is averaging, it is ensembling the synthetic data points. It explains this patient only because it is the local explainability why this person has been detected as a malignant or not. How it interprets large irregular nuclei is driving the results towards the malignant. Smoothness slightly supports benign. If the cells are smooth, then they support benign. Line explains the decision locally by approximating model around this patient by considering the perturbation patient data. So we can see the LIME explanation for the breast cancer. The blot has been given up over here, and the feature, only 4 features are considered among the available features. The mean radius is contributed as 0.42. The mean concativity has contributed as 0.31. Mean area has contributed 0.25, and smoothness has contributed 0.06. So this is the smoothness is only contributed that the cell is benign, whereas other parameters, other features has contributed negatively. So therefore, it explains that the breast cancer, that is malignant case, has been identified. So this mean radius, mean concativity, and mean area, they pushes towards the negative results, and only smoothness pushes towards the positive results, that is benign cells. On the same background, we use the SHAP explanation or SHAP theory, which is the game theoretic. Here the players are the mean radius, mean concativity, mean area, and mean smoothness, and the result is whether the malignant or whether the benign cells. As we calculated in the financial loan applications, they calculate the Shapley values for each of these parameters: radius, concativity, area, and smoothness. And the SHAP values are coming like this: 0.45, negative 0.32, negative 0.28, and positive 0.05 or 0.6. So it is calculated. This equation we had already understood. F of x is equal to phi naught plus summation of all features 1 to m and their phi I. The base value is calculated for the entire model, average benign, that is positive results. That is 0.62% from the data set is having the benign probability. That means non-cancerous cells. So the final probability for this model, we are considering this phi naught minus phi naught plus phi 1 plus phi 2 plus phi 3 plus phi 4. So we are adding summative this summing up all of these results or all of these SHAP values, and we get the final probability as 0.12. So this has resulted the malignant cell. So major contributor is this mean radius, which has contributed in the negative direction 0.45, which indicates the strong malignant signals. The mean concativity has given -32, that is irregular boundary. Mean area is 0.28, that is large nucleus, and the smoothness is towards the positive, is a slightly benign support. Only one feature, only one parameter has given us the benign value. Again, we plot these particular results using the SHAP waterfall plot. It is called as waterfall plot because we are comparing against the base value and which features are towards negative and which features are towards positive. The radius pulls strongly towards the malignant because the radius value is 0.45. Concativity adds more risk, that is this is 0.32. The area reinforces decision, that is 0.28. It confirms how long that particular cell has been affected, and final prediction is towards the malignant. If we are comparing smoothness, the additive equation based on this, so it is giving you the results towards the malignant. The SHAP shows how evidence accumulates the step by step, why this particular case is malignant or not. So if we compare according to the medical context, the Lyme versus SHAP, so both of them has the clinical interpretation. The doctor learns the decision driven by large nucleus and high concativity. These two are the major players, and that has been driven toward the malignant cell. It matches the known pathology patterns for the mammography, for the ultrasound, or for the biopsy kinds of patterns. This XI supports the doctor but does not replace diagnosis. So they assist, XI assist, which are the parameters which are contributing very highly for the malignant, or which are the parameters which are driving towards the benign cells. In summary, the breast cancer detection model learns numerical expressions of cells, cell morphology, whereas the line explains the individual predictions approximately, and the SHAP provides fair additive explanations to align with the clinical reasoning. Remember that the SHAP is additive, SHAP is aggregate, but line explains only one prediction, only one particular case, not the entire data set. If we compare both the applications, both the case studies side by side, the loan approval in the finance domain and the breast cancer detection in the healthcare domain. In the loan approval, the problem was predict loan approval and what decision impacts for the customer trust. And the breast cancer problem predicts benign versus malignant tumor and decision impacts patient safety. So see the problem in the finance, decision impacts customer trust. I should understand why my loan is been rejected, because I am in the need for that particular loan. And for the second, medical healthcare, if I am not having some kinds of symptoms, but I am detected with the breast cancer. So it impacts on the patient's safety. Input features in this case study is considered as age, income, credit score, and existing loans. Input features considered in the breast cancer is mean radius, mean area, concavity, and the smoothness. In both of these case studies, the model is used for the random forest classifier. Prediction here, the loan is rejected, and prediction here, the malignant. Both the case studies has given the negative results. Although the applications are completely different, but explanation logic is identical. The same way we are calculated the Lyme values and SHAP values for the loan approval, and the same way we are calculated Lyme and SHAP values for the breast cancer detections. In the both cases, the model makes the prediction and XAI explains it using for the feature contributions. In the breast cancer, the mean radius, mean area, and concavity has contributed towards the negative, and smoothness is contributed towards the positive. Whereas in the finance application, income, credit score, and existing loans are the driving force towards the negative decision, and the age is only on for the positive direction. This shows that XI is not domain specific. It is a universal framework for the trustworthy AI. So this is the two case studies, and there are, apart from these two case studies, there are various real world applications which demand for XAI, explainable AI. As we see the healthcare, the most impactful decisions are present in the healthcare, such as cancer diagnosis, radiologies, ICU risk. So why we need this XI? Because we need the trust, because we need the safety, because we need the clinical validation. If one doctor is saying that you had been diagnosed for this disease, we are taking the second opinion, third opinion, and so on. And we are averaging that, we are ensembling this, and to get the final decision whether to opt for the surgery, whether to get admitted in the ICU or not. In the finance or banking, the loan approval, credit scoring, fraud. So these are the issues needs to be understood, needs to be addressed. It needs it needs fair and legal justifications. If the same case has been approving the loan and the same case is rejecting the loan, so what is the fairness among that particular the two cases? Autonomous vehicle. The area that needs to be understood is the braking, obstacle detection, when the vehicle should stop because it's driverless or autonomous vehicles in the mining or in terms of sensitive areas. So what it needs, the safety and the accident analysis. So here also we need the explainable AI. Why the autonomous vehicle has blocked, which object has been detected as an obstacle or not, whether these objects are prone to the accidents or not. In cybersecurity also, the intrusion and fraud detections are the key players. So what we need, the alert validation, whether we are getting the false alerts or whether we are getting the true alerts. How we are to these alerts, how we are responding, response clarity, whether the response is to avoid the intrusion or whether the response is after the intrusion. Hiring and HR analysis, most HR is using the resume screening, AI-based resume screening, and the candidate ranking kinds of features. So what is needed? The bias prevention. The HR should not be biased on a particular feature for recruiting that particular person. The HR also needs to follow some ethical considerations is necessary. Next one is the criminal justice. In the criminal justice, risk assessment, parole decisions for the particular person who has been given for some kinds of imprisonment. Why it is needed? The accountability and transparency for those particular decisions. The recommendation systems, we typically use this in Amazon or the Flipkart kinds of applications. The media platforms such as Spotify, if we listen for a song for a particular genre, we get the similar suggestions from that particular genre. So why we need this? We need the user trust and the engagement. And based on this, the other platforms are popular or not popular. whether this particular engagement is true or whether this particular engagement is false. In the industrial or IoT applications, the predictive maintenance is necessary and the actionable insights are required. Industrial or IoT kinds of such as weather forecasting applications. So we need these accountable insights. In the education, it is required everywhere. The student performance predications. So we are just indicating the student performance only based by only by his or her mark or his or her performance in the examination. But these are not two parameters. Marks are the not parameters. There are different parameters needed for the ethical evaluation, whether the student performance is satisfactory or not satisfactory. The government and the public policy, the welfare eligibility, tax funds, tax frauds, etc. Welfare means whether what the government is giving the benefits to a desired person, appropriate or exact person or not. So here also we need the public accountability and ethical considerations. So this is only in nutshell. I have just listed 10 applications. There are so many applications where the explainable AI is useful. The explainable AI summary and the future directions. What XAI is, we already understood. XAI explains why an AI model makes the decision, whether the model be a positive direction or the negative direction. It turns the black box predictions into human understandable reasoning. So we need the answers to these questions. If I diagnose that particular case, what is the reason for that particular diagnosis? Similarly for the financial applications, similarly for the stock applications, similarly for the different areas applications. Why XI is needed? Because the high accuracy is not enough. My model is saying that my accuracy is 94%, 96%, 92%. But this 92% accuracy is not explaining why the results, why this particular classification has taken care. Because it is required the trust, transparency, accountability, ethical issues. So all of these issues should be addressed based on that particular domain. What AI provides? AI is not replacing any existing model, but the feature level explanation is an added layer in terms of Lime or SHARP or some other techniques that we had already just seen, GradCam or some kinds of techniques. It provides the local and global understanding. Local for one particular case, global is for the entire model, entire data set, how the model is behaving. The decision justification is essential, not only necessary, essential in high risk domains such as healthcare. If the decision has been taken, this justification has to be given in terms of trust, in terms of transparency, in terms of accountability. So what it does in the things, the AI predicts, XAI explains, and human decides. So these three terms are frequently used. AI model predicts, explainable AI explains why this decision is taken up, and we human has to decide whether this results or whether this decision should be accepted or not. Even though we are having the various advantages of XAI, XAI is not free from the limitations. Explanation is not equal to casuations. Does mean that it is giving the explanation in terms of the features which are known to that particular model. The features which are unknown, that is human specific kinds of features are unknown to that particular model. Those cannot be explained. Those cannot be considered. Some methods are approximate. SHARP, Lime, GradCam, they are approximate methods. They are very, very sensitive to noise. If perturbation is added towards the SHARP, it is not giving you the better results. Again, if we look for the equations or if we look for the libraries available, they are computationally expensive if the data set is very, very huge. So human interpretation can still be biased. It does mean that I'm saying that you have the 3 loans and you have your income is very less, and because of that my model has rejected your loan application. But it can be still biased because the rules has been defined by the human itself. If the loan application is greater than 2 or the income is less than 40,000. These the rules are defined by the humans, by the programmers. So it can be still biased. XAI explains the model, but not the truth. What the model we had implemented, which features we have discovered, and which feature has contributed. So this is the only limitation. This is the boundary for the XI, but it is never giving you the truth. Currently, the lots of work is going on in the research and development directions, such as the causal explainable AI. So the reasoning towards the cause effect reasoning, what caused the decision? Earlier, we are answering the questions that which feature has contributed, but what caused the decisions? This is critical for the healthcare, policymakers, and the laws. Human-centered AI is another area, whether the explanation is tailored to the professionals, that is the users, doctors, banking officers, engineers, which should focus on the clarity, usability, and cognitive fit before and after taking the decisions. Regulation-driven AI. This is the regulatory information, regulatory the rules such as food and drug industries or food and drug administrators, IRDA insurance regulatory authorities, and so on. So this explanatory becomes mandatory for the regulatory driven explainable AI. It should comply with AI governance and ethics framework designed by those regulatory agencies. They should follow the standardization explanation formats in that particular things. Robust and reliable explanations, stable explanation across the noise and the model updates. If we are performing some analysis using one particular model, and if we upgrade that particular model, if we change that particular model, the decisions or the explanation should not change. It should be robust. If we add some unknown data set, unknown samples from the data sets, the model should give me the predictable results. Evaluation metrics for the explanation quality. This is another area, multimodal explainable AI. So explaining models using text, images, audios, and videos. In the case studies, we have seen only the numerical features, text-based features, but it should also address the image features. It should also address the audio or video kinds of features. It is typically needed for the social media, surveillance, and the healthcare kinds of AI. The last one is the interactive and real-time explainable AI, which allows us for the live explanation and what if counterfactual analysis is necessary. So they are user-driven explanation systems, such as the intrusion detection or the firewall-based systems in the computer networks. The future of AI lies in the model, but not only the accurate, but also transparent, accountable, and human understandable. AI is moving very rapidly, very fastly. We are aware about this AI, how the AI is impacting our life, but no one can making sure that whether the results are transparent, whether the results are trustworthy or not. So these are the some directions. And finally, to conclude, the modern AI models are accurate but opaque. The explainable AI makes AI transparent, trustworthy, and accountable. It is essential nowadays for the high-risk domains such as healthcare, finance, autonomous systems, and so on. The methods like SHAP and LIME helps to understand why decisions are made, which helps, not bridges, which helps to bridge the gap between AI and human reasoning. The human-centered AI is ethical, sustainability, and trustworthy. Technology augments it. Ethics makes the responsibility and transparency, and the human algorithm explainability and interpretability in terms of technical wordings. The future of AI is not just making the correct predictions, but about making decisions that the humans can understand and trust. We used some references for various categories: foundation of XAI and interpretability, LIME, SHAP, healthcare and breast care diagnosis, the case study that we had taken, the machine learning models, the book for the random forest, and ethics and trustworthy related AI. So European Communication has published their ethic guidelines for the trustworthy AI in 2021. So that's it in nutshell for explainable AI. So thank you for your time and participation. Do you have any questions? Let's open the discussion
Thank you,
forum.
sir.
And thank you, ma'am.
Thank you, sir, for delivering an impactable session on explainable AI. Your session has been provided valuable perspectives on how AI decisions can be interpreted, validated, and responsibly implemented in real-world applications such as healthcare and financial sectors. This session marked meaningful and insightful conclusion to this segment of faculty development program. Now, I request participants to post their questions in their chat box, or you can unmute yourself and ask the questions. Yes, participants, if you have any questions, you can unmute yourself and you can ask the question. Okay, we will move forward. Now, I request Professor Pallavi Panda ma'am to give vote of thanks for today's session. Madam,
Thank you, ma'am.
please.
Yes, am I
Just 1
audible,
minute,
ma'am?
madam. Just 1 minute.
Yes.
Yeah,
Okay, sir.
yes, yes.
Hello. I'm really thankful to my friend and colleague, Professor Amulji Patil sir, for giving a very detailed and nice explanation on explainable AI. Rather, there are so many participants who are not knowing related to this term, but he has given a very detailed explanation as well as he have given the future scope, direction, how to do it. So thank you very much, sir. Thank you.
Thank you, Amol sir.
Madam, please
Yes, sir.
continue.
Am I audible, sir?
Yes, you
Yes.
are audible.
Yes, respected dignitaries, esteemed resource person, faculty members, and dear participants. As we come to the end of this enlightening session on explainable AI, it gives me immense pleasure to propose the vote of thanks. On behalf of the Sri Siddheshwar Women's College of Engineering, I extend my heartfelt gratitude to our distinguished resource person, Mr. Amol Patil sir, for delivering such an insightful and engaging session. Sir, your explanation of explainable AI concepts, practical perspectives, and real world application and also the limitations of XAI is truly enriched our understanding and inspired us to explore this emerging domain further. Your expertise and clarity made complex ideas accessible and meaningful. I also thank all the participants for active participation and organizing committee for smooth conduction of session. With permission of dignitaries, I conclude the session. Thank you all. And also I request all the participants that next session will begin at 2 p.m. So join sharply at 2 p.m. using the same link. Thank you, ma'am.
Madam, this is A.G. Patil.
Yes, sir.
Hello. Can we
sir.
have one photograph with camera up on?
Yes, yes.
Yes. I request all participants to on their camera. Kindly on your camera, please.
Amol Phatak sir, turn your camera.
Actually, at the end of every session, they are requesting participant to on the camera. But I think maybe madam has
Forgot.
did it, and thank you for Amul Patil sir for reminding us. Thank you. And please take a screenshot.
Taken?
Yes, sir.
Thank you, ma'am.
Thank
Please
you.
share
Thank
it
you
with
so
the-
much, sir.
Yes, sir. Thank you.
Yeah, yes, sir. Yes, sir.
Yes, sir, yes, sir.
Thank
Thank
you,
you, Pathak sir.
Thank you all. Thank you.
Yes, yes. So shall I leave now?
Yes, sir. Yes.
Yes, sir. Yes, yes. Yes, feedback link of this session has been shared through chat box. You can fill that feedback form. All participants are requested to fill the feedback form.
And
And the next session will be started at sharp 2 p.m. So it's kind request all participants to log in at 1:55 p.m. with the same link. So shall we conclude this?